There are 200 sextillion stars in the observable universe. Each one is a nuclear furnace, releasing the energy of billions of hydrogen bombs every single second. The total fire burning across this cosmos exceeds anything a human mind can meaningfully grasp. And yet, if you stepped beyond the thin shell of Earth's atmosphere and looked out in almost any direction, you would see nothing. Pure, overwhelming blackness. Not dim, not faint. Black. The universe is ablaze, and it still looks empty. The darkness of space is not simply the gap between bright things. It is a message. And what that message tells us about reality is far more unsettling than anyone expected. Pick any direction in the sky and start counting stars. You will run out of patience long before you run out of stars to count. The Milky Way alone holds somewhere between 200 billion and 400 billion of them. Step outside on a clear night, far from city lights, and you might spot a few thousand with the naked eye. That seems like a lot, until you realize you are seeing less than 100 millionth of our galaxy's total population. Point a telescope at any seemingly empty patch of sky, and more stars emerge. Point a professional observatory at that same patch, and thousands more appear. Point the Hubble Space Telescope at the darkest, most vacant speck imaginable. A region so small, you could cover it with a grain of sand held at arm's length. And even there, you will find 10,000 galaxies stacked behind one another across billions of light years. And our galaxy is just one of roughly 2 trillion galaxies scattered across the observable universe. Every single one of those stars is a thermonuclear engine, fusing millions of tons of hydrogen into helium every second, radiating light outward in all directions at 186,000 miles per second. Stars are being born right now inside collapsing clouds of gas. Stars are dying right now in supernovae that briefly outshine their entire host galaxies. There are red dwarfs that have been burning steadily since before Earth existed and will continue burning for trillions of years after our sun is gone. If you could somehow add up the total energy output of every star currently shining in the observable universe, the number would be so vast that no human metaphor could contain it. So here is the question that should stop you cold. Why is it dark? Not dimly lit, not faintly glowing. Dark, the black gaps between visible stars, are not the exception. They are the rule. Those empty stretches dominate the sky. And that observation, that casual, unexamined thing you have accepted every night of your life, is one of the most dangerous traps in all of science. Because if you think carefully about what a universe full of stars should actually look like, you quickly realize the dark sky above you makes no sense at all. The logic is devastatingly simple. Imagine a universe stretching out forever in every direction, filled uniformly with stars the way a forest is filled with trees. Pick any direction and draw a line from your eye outward into infinity. If the universe is truly infinite and truly filled with stars, that line must eventually hit one. It does not matter how far it travels. In an infinite universe, there is always another star farther out. Every single line of sight, no matter where you aim it, ends on the glowing surface of a star, not just some directions, all of them. And if every line of sight contains a star, the entire sky should blaze at roughly the average brightness of a stellar surface. Horizon to horizon, the whole sky should be about as bright as the surface of the sun. An inferno with no escape. Night should not exist. Before you dismiss this as absurd, consider how airtight the reasoning actually is. Divide the universe into thin, concentric shells around Earth, each one light-year thick. A shell twice as far away has 4 times the volume, and therefore contains 4 times as many stars. But each individual star in that farther shell appears 4 times dimmer, because brightness falls off with the square of distance. 4 times more stars, each one a quarter as bright. The two effects cancel perfectly. Every shell, regardless of its distance, delivers the same total amount of light to your eye. The Swiss astronomer Jean-Philippe de Chezeaux worked this out with precise mathematics in 1744. Stack infinitely many shells together, each contributing the same dose of light, and the total becomes infinite. The sky does not merely glow, it explodes with brightness. This is not a fringe idea. It is a mathematically sound conclusion drawn from 3 seemingly obvious assumptions: that the universe is infinite in extent, that it has existed forever, and that stars are distributed more or less uniformly throughout it. For most of human intellectual history, all 3 seemed perfectly reasonable. Nobody had evidence the cosmos had a beginning. The stars appeared scattered across the heavens without obvious boundaries. If all 3 assumptions hold, the shell argument holds. The sky should be on fire. The puzzle had been circulating for nearly 250 years before the German astronomer Heinrich Wilhelm Olbers gave it its most widely read treatment in 1823. Thomas Digges had confronted it as early as 1576, suggesting that the most distant stars were simply too faint to see. The shell argument dismantled that escape immediately. What you lose in individual brightness, you gain in sheer numbers, and the totals never decrease. Johannes Kepler took a blunter approach in 1610, declaring that the universe must therefore be finite. Darkness was simply the boundary wall of a limited cosmos. Edmund Halley revisited the problem in 1720 and sided with Digges, arguing that extreme distance rendered distant stars invisible. De Chezeaux had already proven why that failed. Olbers himself proposed that interstellar dust and gas might absorb the light from distant regions before it reached us. It seemed clever. It offered a physical mechanism for the darkness. But it was fatally flawed, and the flaw was identified almost immediately. If interstellar material absorbs starlight, it heats up. Over time, it reaches thermal equilibrium with the radiation passing through it and begins glowing at exactly the same intensity as the stars it was supposed to be blocking. You cannot hide light by putting obstacles in its path. The obstacles eventually become sources themselves. Every escape route had been sealed. The resolution, when it finally arrived, came from the most unexpected place in intellectual history. In 1848, Edgar Allan Poe, a poet, a fiction writer, a literary critic with no formal scientific training, published a lengthy prose essay called Eureka. His contemporaries mostly dismissed it as eccentric philosophizing. Some called it absurd. But buried within its sprawling metaphysical prose was an insight so precise that it would take professional scientists another half-century to independently rediscover. Poe reasoned that if the universe had a finite age, if the stars had not been shining forever, then the light from the most distant ones simply had not had time to reach us yet. The dark gaps between visible stars were not gaps in space. They were gaps in time. The universe was too young for the accumulated light of all its stars to have filled every line of sight. Darkness was not evidence of emptiness, it was evidence of youth. And by extension, it was evidence that the universe had a beginning. The professional scientific community did not catch up for more than 50 years. Lord Kelvin published a rigorous mathematical version of the same conclusion in 1901, to little attention. It was not until Edwin Hubble discovered that the universe was expanding in 1929, and the Big Bang model was confirmed across the following decades, that the full resolution became mainstream scientific understanding. The assumptions behind the bright sky prediction, infinite age, infinite extent, a static and unchanging cosmos, were not minor errors. They were fundamental misunderstandings of the nature of reality. And the dark sky above you, visible every clear night without any instruments at all, had been carrying that message the entire time. Knowing the universe has a finite age explains why the sky is not infinitely bright. But it does not prepare you for just how dark the sky actually is. A universe containing 2 trillion galaxies, each packed with hundreds of billions of stars burning for nearly 14 billion years. You might still expect some kind of background presence. A faint cosmic twilight, a whisper of accumulated starlight washing across every patch of sky. Something subtle but detectable. Something that at least hints at all the fire behind it. The resolution of the paradox tells you why the sky is not blazing. It does not explain why it is so thoroughly, overwhelmingly, and completely black. That requires understanding something else entirely. Something that does not merely limit the light reaching us, but actively destroys it in transit. Space is expanding. Not in the way a balloon inflates when you blow air into it, though that analogy is sometimes used. The fabric of the cosmos itself, the distance between points in the universe, is growing continuously in every direction, at every scale above the gravitational binding of local structures. Edwin Hubble confirmed this observationally in 1929, when he discovered that distant galaxies are moving away from us, and that the farther a galaxy is, the faster it recedes. This was not because galaxies were flying through space like shrapnel from an explosion. It was because the space between them was stretching. The metric of the universe itself was changing, and it has been changing since the very beginning. This expansion has a direct and devastating effect on light. As a photon travels through expanding space, the space it occupies stretches around it. Its wavelength grows longer, and longer wavelengths carry less energy. A photon emitted as blazing ultraviolet radiation billions of years ago arrives at Earth as faint infrared, completely invisible to the human eye and detectable only by instruments cooled to near absolute zero to prevent their own thermal noise from drowning out the signal. A photon that left its source as visible blue light might arrive shifted all the way past red, past infrared, deep into the microwave spectrum. The expansion does not merely dim distant sources the way distance alone would. It fundamentally transforms what those photons are by the time they arrive. The effect is not a rounding error. A galaxy observed at a redshift of 10, well within the range the James Webb Space Telescope now routinely explores, has had its emitted light stretched to 11 times its original wavelength. Photons that left that galaxy as intense ultraviolet radiation arrive at Earth as faint mid-infrared, invisible to every human eye ever born, detectable only by sensors cooled to within a breath of absolute zero. The light did not fade. It was transformed into something unrecognizable during the crossing. But the most dramatic example of what expansion does to light is not a distant galaxy. It is the universe's own primordial glow. About 380,000 years after the Big Bang, the cosmos cooled enough to become transparent for the first time. Before that moment, the universe was a dense plasma so hot that photons could not travel any significant distance before being absorbed and re-emitted. When the temperature finally dropped enough for electrons to combine with protons into stable hydrogen atoms, the fog lifted, and the radiation that had been trapped in that fog was suddenly free to travel. At that moment, the light filling every cubic centimeter of space had a temperature of approximately 3,000 degrees Kelvin, a blazing orange-white glow radiating in every direction simultaneously at the temperature of a red dwarf star. There were no dark patches. There were no gaps. Every line of sight ended in radiance. The bright sky prediction was, for that one brief window in cosmic history, actually correct. The universe was genuinely bright everywhere, all at once. That radiation still exists. Every one of those ancient photons is still crossing the universe right now, arriving at every point in the cosmos from every direction. But 13.8 billion years of expansion have stretched those photons by a factor of roughly 1,100. What was once a blazing orange-white visible glow has been pulled into microwave radiation, carrying a temperature of just 2.725 degrees above absolute zero. You are bathed in it at this very moment. It arrives from every direction, passes through the walls of your home, and touches your skin continuously. You cannot feel it. You cannot see it. No human eye has ever perceived it, or ever will. The universe took the only moment it was ever truly bright everywhere, and stretched that brightness into a ghost so faint it required purpose-built satellite instruments to detect. The one time the cosmos managed to illuminate itself completely, it could not hold that state. The glow lasted a few 100,000 years. The darkness that replaced it has lasted 13.8 billion years and will continue for far longer. The universe did not merely fail to stay bright. It failed in a way that is permanent, irreversible, and accelerating. Because the expansion is not slowing down. In 1998, two independent teams of astronomers studying distant supernova made a discovery that overturned every expectation. The expansion of the universe is not decelerating under the pull of gravity, as everyone had assumed. It is speeding up. Driven by a mysterious component called dark energy, which accounts for roughly 68% of the total energy content of the universe, space is being pushed apart faster and faster with every passing era. Photons that are currently still detectable from the most distant galaxies are being redshifted further with every year that passes. Light that is marginal today will become unreachable tomorrow. Sources visible now will eventually be pushed beyond the observable horizon entirely. Their light stretched past the sensitivity of any instrument that could ever be built. The universe is not merely dark. It is getting darker, and the rate at which it darkens is itself increasing. All of this, the finite age, the expanding space, the relentless redshift, leads to a number. In 2024, scientists used NASA's New Horizons spacecraft to measure it directly. The probe, traveling more than 5 billion miles from Earth, well past the orbit of Pluto, pointed its instruments at 16 carefully selected patches of deep sky, chosen specifically to avoid contamination from nearby stars, galactic light, and the faint haze of interplanetary dust that plagues every measurement taken from the inner solar system. Then they measured the total optical brightness arriving from the cosmos. The result was approximately 11 nanowatts per square meter per steradian. Sit with that number for a moment. That figure represents the accumulated light of every galaxy that has ever shone across nearly 13 billion years of cosmic history. 2 trillion galaxies, hundreds of sextillions of stars, almost the entire age of the universe, and the combined product of all of it is so faint that it required a spacecraft at the edge of the solar system, the most sensitive instruments available to modern science, and months of careful calibration just to detect it. No human eye could perceive it under any conditions that have ever existed or could ever exist on Earth. The researchers confirmed that this measurement matches the total light expected from all known galaxies. There is no mysterious excess, no hidden reservoir of undetected photons flooding the cosmos from unknown sources. What you get is what the galaxies produce. And what the galaxies produce, from any human perspective, is nothing. The fire of 200 sextillion stars, filtered through the physics of expansion, redshift, and time, arrives as a whisper so faint it has no analog in daily human experience. The darkness does not merely win. It wins by a margin so vast that calling it a competition at all feels dishonest. The finite age of the universe and the expansion of space together explain why the sky fails to blaze. But neither one captures the third layer of the darkness, the one that operates at every scale simultaneously, from the interior of a single atom to the largest structures the cosmos contains. Because the universe is not merely vast, it is structured at every level of magnification around emptiness as the dominant condition. The void is not what fills the space between interesting things. The void is what the universe is made of, and darkness is simply what the void looks like. Start at the smallest scale. Everything you have ever touched is almost entirely made of nothing. Your hand, the surface beneath your feet, the planet beneath that surface. Every atom of every object that has ever existed is overwhelmingly empty space. A hydrogen atom, scaled up until its nucleus was the size of a marble placed at the center of a major city, would have its single electron orbiting as a speck of dust somewhere near the suburbs, roughly half a kilometer away. The arena between them is all vacuum. The atom is more than 99.9% empty space. You are not a solid object moving through the world. You are emptiness held together by forces, walking through more emptiness on a planet made of the same. This is not an atomic curiosity. It is a preview of the pattern that repeats at every larger scale in the cosmos. Step up to the solar system. We carry an image of it in our heads as a compact family of worlds clustered around a central star. A tidy arrangement of orbiting spheres within a manageable neighborhood. The physical reality is something else entirely. If the sun were reduced to a glowing dot on one end of a football field, Earth would be a microscopic speck a few yards away. Jupiter would sit at the far end of the field. Neptune would be somewhere in the parking lot beyond. And the Oort cloud, the outermost region where comets drift in cold, slow orbits, extends a full light year from the sun, nearly a quarter of the way to the nearest star. Within that enormous volume, the total mass of every planet, moon, asteroid, and comet combined amounts to less than 0.2% of the sun's own mass. Everything else is void. If you built an accurate scale model of the solar system and tried to see the planets with the naked eye, they would be invisible. Not small, invisible. The distances dwarf the objects by factors so extreme that the objects themselves effectively disappear. If the sun were switched off tonight, the darkness inside our own solar system would be nearly indistinguishable from the darkness of deep interstellar space. Step beyond the solar system, and the emptiness becomes something harder to hold in the mind. The nearest star to our sun is Proxima Centauri, at a distance of approximately 4.24 light-years, roughly 25 trillion miles. A spacecraft traveling at the speed of the Voyager probes would need more than 73,000 years to complete that crossing. And Proxima Centauri is close. It is the nearest star. In the outer regions of the Milky Way, neighboring stars can be separated by 10 or 20 light-years. In the galactic halo, individual stars orbit in near total isolation, separated from their nearest companions by hundreds or thousands of light-years of void. The interstellar medium filling the space between stars is not truly empty in the strictest physical sense. It contains a thin scattering of hydrogen atoms and the occasional dust grain. But the density is almost incomprehensibly low, roughly 1 atom per cubic centimeter. Compare that to the air you are breathing right now, which contains approximately 25 million trillion molecules per cubic centimeter. Interstellar space is a vacuum more perfect by a factor of 10 to the 19th power than the air in your lungs. It is a vacuum more perfect than anything humans have ever produced in a laboratory, achieved across trillions of miles in every direction without any effort at all. If you were placed in the middle of interstellar space with no ship and no suit, The experience would be unlike anything terrestrial darkness prepares you for. No sound, because sound requires a medium, and there is no medium. No pressure, because the density of gas is functionally zero. No temperature you could feel, because there are not enough particles impacting your skin to transfer thermal energy in any meaningful way. You would see stars, bright ones nearby, dim ones farther out. Perhaps the faint band of the Milky Way if you happen to be within the galactic disk. But the overwhelming reality would be blackness. The stars would feel like errors in the fabric of the darkness, tiny accidental exceptions in a field of total absence. And this is the environment inside a galaxy, inside one of the supposedly dense, bright, star-filled structures of the cosmos. The Milky Way contains between 200 billion and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter. That sounds dense. It sounds like a region packed with luminous objects. It is not. If you asked what percentage of the galaxy's volume is occupied by actual stellar matter, the answer would require scientific notation to express. Stars are tiny compared to the distances separating them. Each one a sphere of plasma a few 100,000 to a few million miles across, floating in a void trillions of miles wide before the next one appears. You could remove 99.9% of the galaxy's volume and lose nothing but empty space. The galaxy is not a collection of stars. It is space, with stars as rounding errors. Each one a single lit match in a cathedral so vast that its glow dies long before reaching the nearest wall. Now leave the galaxy entirely and step into intergalactic space. Here the void scales up by another factor of roughly 1 million. The nearest major galaxy to our own is Andromeda, at 2.5 million light-years away. Between us and Andromeda, there is essentially nothing. A scattering of hydrogen so diffuse it barely qualifies as matter, roughly 1 atom per cubic meter, compared to the already ghostly 1 atom per cubic centimeter of interstellar space. Intergalactic space is 1 million times emptier than the emptiness between stars. Temperatures in the deepest voids hover within fractions of a degree of absolute zero. No stars inhabit this gulf, no planets, no structures of any recognizable kind. If you could somehow survive and float at the midpoint between the Milky Way and Andromeda, both galaxies would appear as faint glowing smears on opposite horizons, too distant to resolve into individual stars. Each one a dim suggestion of combined light rather than a source of illumination. Between them, the sky would be the deepest black any conscious being has ever experienced. Not the darkness of a cave where scattered photons from distant entrances still faintly color the air. Not the darkness of the deep ocean floor, where bioluminescence occasionally interrupts the black. Those environments still contain atmosphere, still contain molecules that interact with light in some way. Intergalactic space contains none of that. The darkness there is not the absence of illumination. It is the absence of everything that could be illuminated. An intergalactic space is not even the emptiest environment the universe has to offer. Between galaxy clusters, across the vast bubbles of the cosmic web called voids, the emptiness reaches a depth that makes the gap between the Milky Way and Andromeda seem crowded by comparison. Individual cosmic voids can stretch 300 or even 500 million light-years across. A civilization placed at the center of one would see no galaxies on the horizon in any direction. No faint smears of combined starlight hinting at distant structure. No reference point of any kind. Just expanding vacuum in every direction, growing colder and more diffuse with every passing moment, surrounding them with a darkness so complete and so structural that no technology they could ever build would change what they saw when they looked out at the universe. That is not a remote or exotic condition. Voids occupy somewhere between 70 and 90% of the total volume of the observable universe. The filaments, clusters, and galaxies, all the structure that contains all the stars that produce all the light, occupy a minority of the total volume. Everything else is that darkness, not as a background, as the foreground, as the primary and defining feature of the cosmos at its largest scales. The universe is not a web of light connected by luminous threads. It is a web of darkness, with luminous threads so thin that from a sufficient distance they would be invisible entirely. Everything described so far has been about the mechanisms of darkness. The finite age that cuts off distant light. The expansion that drains energy from photons in transit. The geometry of emptiness that dominates every scale from atoms to galaxy clusters. Each one is individually powerful enough to darken the sky beyond what intuition expects. But the universe does not apply them one at a time. It applies all of them simultaneously, to every photon, from every source, at every distance. And when you stack them together, the result is not a marginal failure of brightness. It is a catastrophic annihilation of light by the combined forces of physics. To feel the weight of that, you need one more tool. One more law that operates without exception on every source of light in the cosmos, near or far, bright or dim, ancient or newly ignited. It is the simplest and most brutal rule in all of physics. The inverse square law. The apparent brightness of a light source decreases with the square of the distance between you and it. Not proportionally, not linearly, with the square. A star twice as far away is not half as bright. It is 1/4 as bright. A star 10 times farther is not 1/10 as bright. It is 1/100th as bright. A star 1,000 times farther away appears 1/1,000,000th as bright. The fall-off is savage. It is merciless, and it applies universally to every source of light in the cosmos, without exception and without mercy. Consider our own sun. From the surface of Earth, roughly 93 million miles away, it is brilliant enough to light entire continents, drive weather systems, and power photosynthesis across a living planet. Now move it to the distance of the nearest star system, Alpha Centauri, approximately 4.24 light-years away. That is roughly 270,000 times farther than the Earth-Sun distance. The inverse square law says the sun's brightness drops by the square of that factor. 270,000 squared is approximately 73 billion. The sun, seen from the distance of the nearest star, would be 73 billion times dimmer than it appears from Earth. It would be a faint point of light visible to the naked eye on a dark night, but contributing effectively zero illumination to anything around it. That single number, 73 billion times dimmer, for the nearest possible stellar neighbor, should reframe everything you think you know about how stars light up the cosmos. And that is the nearest star. Most stars in the Milky Way are far more distant. Stars near the galactic center sit roughly 26,000 light-years away, about 6,000 times farther than Alpha Centauri. Apply the inverse square law again, and their individual contributions to the brightness of our sky become numbers so small they have no physical analog in daily experience. The galactic center contains the densest concentration of stars in the entire Milky Way. Hundreds of thousands of them packed into a region a few light-years across. And from Earth, their combined glow amounts to a faint smudge barely visible to the naked eye on the clearest nights. Hundreds of thousands of nuclear furnaces, and the best they can collectively manage across 26,000 light-years, is something you might miss if you were not looking for it. Now extend this to other galaxies. The Andromeda Galaxy is 2.5 million light-years away and contains roughly 1 trillion stars. 1 trillion stellar furnaces, each converting millions of tons of hydrogen into energy every second. And the result, as seen from Earth, is a dim smudge barely perceptible to the naked eye on the darkest nights. And only then, if you know exactly where to look. That smear of light represents the combined output of more stars than grains of sand on every beach on Earth, reduced by distance to something you could easily overlook. And Andromeda is our nearest major neighbor. The Virgo cluster, the nearest large collection of galaxies, sits roughly 54 million light-years away, more than 20 times the distance to Andromeda. The inverse square law punishes that extra distance with savage efficiency. 20 times farther means 400 times dimmer per individual star. Individual stars in Virgo cluster galaxies are so thoroughly extinguished by distance that no telescope ever built could detect a single one. Only the combined glow of entire galaxies is visible, and even that requires serious instruments to observe. Galaxies at the edge of the observable universe, billions of light-years away, are reduced by the inverse square law to contributions so infinitesimally small that collecting their light at all requires some of the most extraordinary feats of engineering in human history. The Hubble Ultra-Deep Field, one of the most iconic images in astronomy, required more than 11 days of total exposure time aimed at a single patch of sky smaller than a grain of sand held at arm's length, just to reveal galaxies whose individual stars were utterly beyond detection. 11 days of staring at one tiny point in the heavens, and the galaxies that emerged were still barely visible smudges at the ragged edge of what the instrument could perceive. This is what the inverse square law does at cosmic distances. It takes unimaginable power and reduces it to nothing. It takes 1 trillion stars and turns them into a smudge. It takes that smudge and, given enough additional distance, turns it into something that requires 11 days of staring to confirm exists at all. Now consider what happens when you combine the inverse square law with everything else. The finite age of the universe limits how many shells of stars can contribute light to our sky at all. Cosmic expansion takes the photons that do survive the journey and drains their energy, shifting them out of the visible spectrum entirely. The inverse square law then crushes whatever visible light remains, dropping it by the square of every additional light-year of distance. And underneath all of it, the overwhelming geometry of emptiness ensures that most of space receives almost no light from any source at any distance to begin with. Stack these together, and the result is the number we already encountered: 11 nanowatts per square meter per steradian. That is not a number that emerges from any single mechanism failing. It is a number that emerges from every mechanism failing simultaneously, each one compounding the others, each one making the darkness deeper than any one of them could have managed alone. The finite age cuts off the most distant contributions. Expansion degrades the survivors. The inverse square law buries what remains. And the geometry of emptiness stretches the remnants across a volume so vast that even the degraded, distance-crushed light cannot meaningfully illuminate the space it travels through. To put the scale of this failure into perspective, consider what the numbers actually mean in human terms. The Sun delivers approximately 1,400 watts of energy per square meter to the top of Earth's atmosphere. That is the power of a small space heater arriving every second from a single star at a distance of 93 million miles. The cosmic optical background, the accumulated light of every galaxy across the entire observable universe and nearly the entire history of cosmic time, delivers 11 nanowatts per square meter. That is 0.0011 watts. The Sun outshines the entire observable universe, as seen from outside our solar system, by a factor of roughly 100 billion. One ordinary star versus 2 trillion galaxies containing hundreds of sextillions of stars, burning for nearly 14 billion years. And the single star wins by 100 billion to 1. That is not a close contest. That is not a competition at all. It is a demonstration of what distance, expansion, and geometry do to even the most staggering quantities of fire, when the volume those fires must fill is large enough. The cosmic accounting is brutal, and it is final. There is too much space. There has never been enough fire. And every additional light year of distance, every additional billion years of expansion, every additional cubic light year of void makes the imbalance worse. Human beings evolved on a world where light fills space. Strike a match and the surrounding air brightens. Build a campfire and the clearing glows. Gather enough sources and darkness yields. This conviction is not something we were taught. It is woven into the architecture of our perception. Built into the visual cortex that evolved on an African savanna, where firelight meant warmth and safety. Our brains assume at the deepest level that sufficient fire produces sufficient light, and that sufficient light eliminates darkness. The universe does not work this way. The distances are too large, the expansion is too relentless. The inverse square law is too merciless. A campfire lights a clearing because the clearing is 30 feet wide. The space between stars spans trillions of miles. At that scale, even the most powerful stellar furnace becomes a pinprick, detectable only by instruments of extraordinary sensitivity, surrounded by a darkness it cannot meaningfully touch. Each star is an island of warmth and light, and each island is surrounded by an ocean of vacuum so vast that the light from one cannot warm the waters around the next. This is not a poetic metaphor. It is a physical description. If you could travel to the midpoint between our Sun and Alpha Centauri, 2 light years from each, and measure the total illumination reaching you from both stars, the number would be effectively 0. 2 nuclear furnaces, each converting millions of tons of matter into energy every second, and at the halfway point between them, you are in absolute night. No glow on the horizon, no ambient shimmer, no faint haze, just darkness in every direction, as complete as anything the universe contains. Multiply that scenario across every pair of neighboring stars, in every galaxy, in every filament of the cosmic web. And the picture that emerges is not a universe trying and failing to be bright. It is a universe in which brightness was never structurally possible. The fire exists. It has always existed, and the darkness has always been greater. Not by a narrow margin, not by a factor of 2 or 10 or a million, but by a margin so absolute that the combined output of every star that has ever burned across the entire history of the observable universe cannot produce a background glow that any eye, evolved anywhere, on any world, could ever see, without a spacecraft, a sensitive detector, and months of careful work to find it at all. Everything so far has described the darkness as it exists right now. But there is a dimension to the darkness that is harder to absorb than any of the physics, because it is not about how the universe is structured today. It is about where the universe is going. And where it is going is toward a darkness so total, so permanent, and so irreversible that the current night sky, black as it appears to us, will eventually look, by comparison, like the brightest place the cosmos ever managed to produce, because the era of stars is ending. Star formation across the cosmos peaked approximately 11 billion years ago, when the universe was only about 3 billion years old. At that moment, galaxies were furiously converting cold hydrogen gas into new stars at rates dozens of times higher than anything occurring today. That period, sometimes called cosmic noon, was the brightest the universe has ever been or will ever be. the sky of a planet orbiting a star during cosmic noon, looking out at a young and vigorously star-forming galaxy embedded in a cosmos thick with newly ignited fires, would have been unrecognizably richer than what we see tonight. More stars, more light, more active galaxies blazing with the energy of millions of supernovae. That was the peak. Everything since has been a slow, continuous, irreversible decline. Today, the cosmos produces new stars at roughly 3% of its peak rate. The fire is going out, not suddenly, not catastrophically, but steadily, measurably, in a direction that does not reverse. The fuel is running low. Stars are born from cold molecular hydrogen gas, and that gas was abundant in the early universe, feeding the great stellar boom of cosmic noon. But stars consume gas. Supernovae blast it out of galaxies entirely. Active galactic nuclei heat the surrounding material until it can no longer collapse into the dense, cold clumps that star formation requires. Over billions of years, the reservoirs have been drained, dispersed, heated, and rendered chemically unusable. What remains is increasingly sparse and increasingly incapable of sustaining anything like the star formation rates of the past. Astronomers estimate that more than 95% of all the stars that will ever exist in the history of the universe have already been born. The cosmic factory is not slowing toward a new steady state. It is shutting down. Even if the universe persists forever, no more than 5% additional stars will ever form. The remaining output will trickle out over billions of years, each generation smaller and dimmer than the last, until the last cold gas cloud collapses into the last new star, and the process stops entirely. The last stars to form will be red dwarfs. Dim, patient, extraordinarily fuel-efficient, they burn at a fraction of the intensity of stars like our sun, but stretch their hydrogen supplies across timescales that dwarf everything else in stellar physics. Not a single red dwarf anywhere in the observable universe has yet aged noticeably by its own standards. Every one of them is, by red dwarf reckoning, essentially newborn. They will outlive our sun by a factor of 1,000. They will outlive every blue giant and every yellow star currently visible in the night sky by margins so large the comparison barely makes sense. But eventually, even they run out. The last red dwarf in the last galaxy will exhaust its hydrogen fuel and fade. Not in an explosion, not in a dramatic finale. Just a slow dimming, a cooling, a transition from a faint red glow to a cold dark cinder drifting through space. And when that happens, the stelliferous era, the age of stars, the entire chapter of cosmic history during which nuclear fusion lights the universe, will be over. Astrophysicists Fred Adams and Gregory Laughlin gave it that name. The stelliferous era, the age of stars. It stretches from roughly 1 million years after the Big Bang to approximately 100 trillion years from now. 100 trillion years sounds like an eternity. Against the full timeline of the universe, it is not even a rounding error. What follows is the degenerate era. Stars are gone. What remains are their corpses. White dwarfs slowly cooling toward invisibility. Neutron stars gradually fading. Brown dwarfs, too small to have ever truly ignited, drifting cold and dark through the void. This era stretches from roughly 10 to the 15th power years to 10 to the 39th power years after the Big Bang. Timescales so large they dissolve all human intuition about duration. During this era, the universe still contains matter, but produces almost no light. Occasionally, two white dwarfs might drift close enough to collide, triggering a brief thermonuclear flash that illuminates the surrounding void for a few weeks before fading back to black. These events, are the last gasps of stellar luminosity. Brief, rare, separated from one another by trillions of years of absolute darkness. The universe in the degenerate era is not dark the way a moonless night is dark. It is dark the way the inside of a sealed vault is dark. Structurally, permanently, without any prospect of relief. After the degenerate era comes the black hole era. White dwarfs and neutron stars have long since cooled to invisibility. The only significant objects remaining are black holes, the collapsed remnants of the most massive stars and the supermassive engines that once anchored the centers of galaxies. They do not glow. They do not radiate in any way detectable by conventional means. They simply exist, massive and cold and lightless, embedded in an expanding void from which every other form of structure has long since vanished. This era persists until roughly 10 to the 100th power years from now. A number written as a 1 followed by 100 zeros. A duration so incomprehensibly long that every era of cosmic history that came before it, including the current age of stars, would fit into its opening instant without being measurable. Black holes do eventually end. Through a quantum process called Hawking radiation, they slowly leak energy into the surrounding space, losing mass at a rate so gradual it defies any earthly analogy. A black hole with the mass of our Sun would take 10 to the 67th years to fully evaporate. The supermassive black holes at the centers of former galaxies last far longer. But eventually, one by one, they too vanish, converting their mass into the faintest possible trickle of low-energy radiation, and then disappearing entirely. And when the last black hole evaporates, the black hole era ends. What comes after has a name: the dark era. And the dark era has no end. No stars, no stellar remnants, no black holes, no structure of any kind. Just elementary particles, electrons, positrons, photons, neutrinos, drifting through an ever-expanding, ever-cooling void with decreasing energy and vanishing density, approaching but never quite reaching absolute zero, forever. The dark era does not conclude. It does not transition into something else. It simply continues, growing colder and emptier and more featureless across durations that make the black hole era look instantaneous, that make the age of stars look like a camera flash in the history of an ocean. There is no bottom to the timeline that follows the last black hole's fading. It is an abyss without a floor. Now consider where the stelliferous era, our era, the age in which stars exist, the age in which any light exists at all, sits within this full timeline. If you compress the entire future history of the universe onto a single page, the age of stars would not be a paragraph or a sentence or even a word. It would be a mark so thin that no printer ever built could render it. A line thinner than a single atom on a page, representing eternity. Everything before it and everything after it is darkness. The fire is not the story. The fire is a footnote. We happen to exist during that footnote. We evolved under a sky lit by a middle-aged star in a galaxy that is itself past its period of peak star formation, surrounded by a universe already well into the long declining slope from cosmic noon toward the final darkness. And because the footnote is all we have ever known, we have mistaken it for the normal condition of the cosmos. We look up and see stars and assume brightness is the baseline, that light is the default, that the universe is fundamentally a luminous place, with occasional patches of darkness scattered through it. The truth is the precise reverse. The universe is fundamentally a place of darkness, with a brief, temporary, and already fading interruption of light. That interruption is called the Age of Stars. It has lasted roughly 14 billion years so far, and it has perhaps another 100 trillion years to run before the last red dwarf fades. Then it ends. And what follows is not another kind of brightness or a different form of light. It is the permanent condition that existed before stars and will exist after them. A darkness so total and so enduring that the current night sky, black as it appears to us, would look, by comparison, like the surface of the sun. Every second, our sun converts approximately 4 million tons of its own mass into pure energy. 4 million tons of hydrogen squeezed into helium through nuclear fusion at temperatures exceeding 15 million degrees. The energy released by this single, perfectly ordinary star in 1 second exceeds the total energy consumed by human civilization across its entire history. 1 second of sunlight, more power than every engine, every generator, every fire, every electrical grid, every nuclear reactor humanity has ever built, combined and multiplied by a factor of millions. And the sun is unremarkable. It is a middleweight star in a galaxy that contains hundreds of billions of them. Blue supergiants burn hundreds of thousands of times more fiercely. Across the observable universe, stars in every stage of life and death pour energy into the void with a ferocity that defeats every metaphor. The total luminous output of the cosmos is approximately 3 times 10 to the 49th watts. Written out in full, that number stretches past comprehension long before you finish counting the zeros. And yet the universe is dark. Not slightly dim, not faintly glowing. Dark in a way that required a spacecraft 5 billion miles from home to even measure the accumulated glow of all of it. This is the central truth that the darkness of space forces you to confront. And it contradicts everything human intuition has ever suggested about the relationship between fire and the space it occupies. We evolved on a world where light behaves the way we instinctively expect it to. Strike a match and the surrounding air brightens. Build a fire and the clearing glows. Fill a room with enough candles and every shadow retreats. In human experience, light fills space. It radiates outward from its source and conquers the darkness around it. Given enough sources, darkness yields. This is not a belief we were taught or a conclusion we reasoned our way toward. It is a conviction embedded in the deepest architecture of our perception, forged over millions of years of evolution on a planet where the presence of light meant warmth and safety, and the presence of darkness meant danger. Our brains do not consider the possibility that enough fire might still not be enough. The assumption is structural. It is below conscious thought. The universe does not honor that assumption. It never did. The distances involved are not merely larger than the distances of human experience. They are larger in a way that places them in an entirely different category of reality. One where the intuitions built on campfires and city lights do not merely fail, but invert. A campfire lights a clearing because the clearing is 30 feet wide. A city glows because its glow only needs to cross a few dozen miles before hitting the next city. In those environments, enough sources do produce enough light. The scale is human. The physics cooperates. But the space between stars spans trillions of miles. The space between galaxies spans quintillions. At those distances, the inverse square law does not merely dim a source. It obliterates it. Even the most powerful stellar furnace, seen from the midpoint between itself and its nearest neighbor, contributes illumination so close to zero that no instrument sensitive enough to detect it has ever fit inside a human hand. The light does not fill the surrounding space. It does not even dent it. Each star is surrounded by a sphere of influence so small, relative to the void enclosing it, that describing the ratio requires scientific notation. And what is true between individual stars is true at every larger scale. Between galaxies, between clusters, across the cosmic voids that occupy the overwhelming majority of universal volume, the light from every source in existence arrives so attenuated, so red-shifted, so crushed by the combined forces of distance and expansion, that it registers not as illumination, but as a faint statistical signal, detectable only after enormous effort. The universe is not a place where light happens to be losing a close race against darkness. It is a place where the contest was decided by the laws of physics before the first star ever ignited. Written into the geometry of space, the speed of light, and the age of the cosmos from the very beginning. No amount of additional stars would change this. That is the part that is most difficult to accept. The instinct says that if the universe simply contained more stars, or brighter ones, or more densely packed ones, the darkness would eventually yield. But the volume of space grows faster than any population of light sources can fill it. Add more stars, and you also add more space between them. The ratio does not improve. The darkness does not retreat. In an expanding universe where space itself is the canvas and light is the paint, the canvas always wins, because the canvas grows and the paint does not. Consider what it means to stand outside on a clear night and look up. You are receiving, in that moment, a message that has been waiting for you every night of your life. The message is not encoded in the starlight, though the starlight carries its own information. The message is in the darkness between the stars, in the black gaps that dominate every patch of sky, that stretch between every point of light, that persist no matter how powerful a telescope you point at them or how long you expose your detector. That darkness is not a gap in the picture. It is the picture. The stars are the interruption. The blackness is the canvas. And the canvas is nearly everything that exists. What makes this harder to absorb than any of the individual physics is the sheer completeness of it. The darkness is not a local condition that happens to surround our particular corner of the cosmos. It is universal. An alien civilization in a galaxy 5 billion light-years from here, orbiting a star in a region of space we will never observe, looking out at their own sky, would see the same thing. Darkness between their stars, darkness between their galaxies, darkness stretching in every direction toward a horizon they can never reach. It would not matter how advanced their technology was or how sensitive their instruments were. The darkness is not a problem of detection. It is a property of the cosmos. No location in the observable universe is bathed in ambient starlight. No world anywhere receives meaningful illumination from the combined glow of distant stellar populations. Every inhabited planet, every possible civilization, every conscious being that has ever existed or could ever exist, looks out at a sky dominated by blackness. The darkness is not a local condition. It is the one experience every observer in the cosmos must share. And the darkness is growing. Star formation is declining. The cosmic fuel supply is running out. The expansion of space is accelerating, pushing sources of light beyond the observable horizon one by one, erasing them from the sky of every future observer. The universe is not moving toward a brighter equilibrium. It is moving away from one. Cosmic noon was 11 billion years ago. Everything since has been a slow dimming. Everything ahead is a faster one. There is a detail in the future timeline of the cosmos that carries a particular weight. Eventually, the accelerating expansion will carry every galaxy beyond our local gravitationally bound group, past the observable horizon. The Virgo cluster, the Coma cluster, every distant structure currently visible in our deepest telescope images will recede beyond the reach of light and vanish. a civilization arising in the far future, after that process is complete, will inherit a sky containing only the merged remnant of the local group. A single island of aging stars surrounded by perfect, featureless blackness in every direction. They will have no way of knowing the universe was ever anything else. The cosmic microwave background will have been redshifted into undetectability. The evidence for the Big Bang will be gone. The expansion of the universe will be unmeasurable because there will be nothing left to recede. They will look out at their single island of stars in an otherwise empty cosmos and conclude, reasonably and incorrectly, that this is all there is and all there has ever been. The darkness will have swallowed not just the light, but the memory of the light. The cosmos will have erased its own history. We do not live in that future. We live in the one brief window when the evidence is still present, when the cosmic microwave background still whispers from every direction, when distant galaxies are still visible across billions of light years, when the full scope of the universe is still available to any instrument patient enough to collect the light. We live, cosmologically speaking, early enough to see what the universe is and where it came from, and what it is becoming. And what it is becoming is dark. The fire is real. The stars are real. The energy pouring out of every stellar furnace in every galaxy across the observable universe is real and staggering, and beyond all human capacity for comparison. And none of it is enough. It has never been enough. The darkness does not merely win. It wins at every scale, in every direction, across every epoch of cosmic history. By a margin so absolute that the combined output of 200 sextillion stars burning for nearly 14 billion years produces a background glow too faint for any eye to see. Every night, without instruments, without effort, without any scientific knowledge at all, you can confirm this with your own eyes. Step outside. Look up. The stars are there, brilliant and ancient and real. And between them, dominating everything, winning without contest, is the dark. Not as an absence, not as a failure of the light to arrive, as the natural, structural, inevitable conditions of a universe built from expansion and separation and finite time. A universe where distance is more powerful than brightness, and emptiness is more fundamental than matter. And the void was always going to outlast the fire. The darkness is not what the universe is missing. It is what the universe is. And it has been telling you that every night of your life. There are 200 sextillion stars in the observable universe. Each one is a nuclear furnace, releasing the energy of billions of hydrogen bombs every single second. The total fire burning across this cosmos exceeds anything a human mind can meaningfully